esto, pues quería presentar al ponente de hoy, que es José Manuel, ¿no? Que es un electroquímico de la Universidad de Córdoba, que ha estado con nosotros 2 años, ¿vale? Que os voy a mencionar un poco, pues como tengo memoria de pez, os digo, os leo un poco su trayectoria, ¿no? Él defendió su tesis de manera compartida entre Madrid y Zaragoza en los institutos de carboquímica y de catálisis de petroleoquímica del CSIC, ¿no? Sobre las temáticas de desarrollo de catalizadores basados en grafeno modificados con nanopartículas metálicas para su aplicación en dispositivos de conversión electroquímica. De ahí, pues, bueno, su formación, ¿no? Ha realizado estancias postdoctorales en el CNR italiano, ¿no? También hay para dispositivos de almacenamiento y no de conversión de energía, ¿no? Entre el 21 y el 23 participó en la plataforma Transener, ¿vale? Y estuvo implicado en el desarrollo de un módulo autónomo de batería de flujo, redox, de vanadio, de una potencia de 50 kilovatios, y también en el desarrollo de un electrolizador de agua de 5 kilovatios de membrana polimérica, que fue a partir de lo cual pues nos conocimos, y en 2023 pues se incorporó con nosotros en el instituto, ¿no? Para el desarrollo de catalizadores depositados por vacío, para su implementación en electrolizadores de la misma tecnología, de membrana alcalina, y su trabajo ha estado, digamos, en el marco de un contrato con una empresa H2B2 con la que venimos trabajando desde hace 3 o 4 años. ¿Vale? Y hoy nos va a hablar, pues, de su último trabajo que ha hecho con nosotros, que nos lo va a contar ahora mismo. 20 minutos.
Creo que no tiene ahora. Oh, se oye. A lo mejor, si me lo lees un poco. Sí. Creo que no tiene batería, se apaga. ¿Se escucha así? Más o menos. Hola. ¿Así? ¿Así? Es que... No. Vale. Ya estamos bien, ¿eh? Si lo pongo así, ¿se oye más o menos? Vale. Ok. Empiezo otra vez. Thank you so much for coming today. I will start my presentation, which is entitled Ion number 3, nickel iron oxide bilayer oxygen evolution reaction electrocatalyst prepared by magnetron sputtering in oblique angle deposition methodology. This is the title of our latest paper, but I will divide this presentation in 2 main development lines that I have been performing here in the group. The first one is the fabrication of electrodes with relevant size for large-scale application by using the methodology developed previously by the group. And the second line is the development of this bilayer catalyst, which combine the 2 formulation of metallic nickel iron and metallic nickel oxidized nickel iron to improve the electrocatalytic behavior of the catalytic coatings prepared previously by the group. So as many of you probably know, in our group we are focusing the use of PVD techniques for the deposition of thin fields with multiple applications, and in this case we use the technique of magnetron sputtering for the preparation of catalytic coatings and its application in the water electrolysis technology. So I won't explain the fundamentals of this technology because I suppose that you already know it. But I would like to remark that this technology have a major advantage compared to the traditional wet route for the preparation of catalytic coatings, which is that we can manufacture or synthesize and deposit our catalytic layer in only one step by a simultaneous procedure. This is relevant because this helps to control the composition of the layer, its thickness, and also we can modulate its property to make it more active for our application. And additionally, this is a technique that is widely implemented in the industry. So it's a technique that is very proper if we want to obtain electrode with large scales, or if we want to deposit large scale or large amount of surface, and then obtain a big amount of electrode that will be used in the industry. To summarize, it's a technique that is highly scalable. So this work started previously with the development performed previously by our colleagues Esther and Celia during their PhD thesis work, and they conclude that the best combination of cathode and anode for an application in a water electrolysis system is the use of metallic nickel in the cathode to promote the hydrogen evolution reaction, and a metallic combination of nickel iron in the anode to promote the oxygen evolution reaction. Here you can see how these kind of catalytic coatings are deposited over a porous transport layer, a commercial porous transport layer, and here you can see how this catalytic coating is distributed among this fiber, depicting a mesoporous structure that is formed by these nanocolumns that grow from the bottom of the substrate to the top. One particular characteristic of this kind of catalytic coatings is that doesn't have any kind of ionomer, which is a molecule that usually is used in this kind of catalytic formulation when they are prepared by wet routes that help to fix the catalyst to the substrate. In our case, this is not necessary, so we simplify the procedure of deposition, and also we avoid possible degradation that is promoted for this kind of molecules that normally are not stable in alkaline media. So if we use this combination of cathode and anode in a small prototype water electrolyzer of 5 square centimeters of area, we can see the performance comparing the responsive voltage at different current densities. These two values that I have marked as standard values in the literature for different current densities are more or less in the average value for this kind of formulation prepared by wet routes, but with the particularity that we don't have neither PGM-free catalyst and nor ionomer, and our amount of catalyst deposited by this technique is so low. So we have 3 advantages compared with the catalysts that normally are prepared by wet routes in the literature. Additionally, we were able to measure the amount of hydrogen that we were producing with this prototype, and we are testing batch in our laboratory, and combining the power density measure in this curve with the amount of hydrogen produced, we can calculate the efficiency of our system, which is more or less around 65% of efficiency for the production of hydrogen. This value is more or less in the average of the with other similar systems reported in the literature. And this efficiency is translated in a specific power consumption of more or less 60 kilowatts per kilogram of hydrogen produced. more or less, this is translate that the cost of, if we use more or less a 0.14 cent per kilowatt, this indicates that our hydrogen more or less cost around 6 to 9 euros to produce 1 kilogram of hydrogen. So at this point, with the development performed by Esther and Celia and the measure that we did in our laboratory, we conclude that this catalytic coating were able to be introduced in a water electrolysis system. So we need to scale up the production to prepare a big scale prototype of water electrolyzer to produce more amount of hydrogen, of course. So to do this, we choose industrial magnetron spattery chamber, as the one that is shown here, that allow us the possibility to obtain electrode of bigger area. This is an electron of 9 centimeter of diameter, which is translated in 74 square centimeter of area. Remember that the previous one was 5 square centimeters, so we have multiplied the area by 12, 13 times, and we can obtain up to 100 electrodes per batch. So we are increasing to magnitude orders the capability of for the deposition of catalysts from the square centimeter to the meter centimeter. So we now can obtain a big amount of electrode with this chamber. If we compare the structure of the catalytic coating deposited in our laboratory with those obtained in this chamber, here we have 3 examples of 3 different electrodes, and here is our electrode deposited here. We can see how the columnar structure remains in both the laboratory and the scale-up chamber, and the structure of the catalytic layer over the fibers are quite similar with these agglomerates and this mesoporous structure that I described before. So at this moment we have the electrode, but we know we need a device to try it, to prove their electrochemical performance. So we manufacture a prototype of alkaline exchange membrane water electrolyzer with 20 cells, and to manufacture it was precise to design the manufacturing planes, and also we had to simulate some experimental conditions as the gases and temperature distribution, and also was needed, of course, to simulate the working behavior of this prototype in a 20-cell stack. We can also see here how we were able to simulate even the oxygen evolution in the exit of the device. So with now we have the device, we have the electrode, so we need all the components that conform the electrode membrane assembly, which is this part of here. This part is inside our prototype, which is here. If you want to see it later, you can come and see it. And by the selection of the better materials, we were able to prepare this membrane electrode assembly, and we are now ready to test it in the prototype. Here I have a group, all the characteristics of this 20-cell stack. It can operate between 1 to 3 kilowatts of power at the current rate between 0.5 and 1 ampere square centimeter of current density, and in this condition it is able to obtain between 0.5 to 1 kilogram of hydrogen by day. To determine its electrochemical behavior, we went to CMAT facilities in where we can use a 5 kilowatts testing bench, and here you can see the voltage current density comparison normalized per cell. So we can see the comparison between our small cell recorded in our laboratory with the behavior of the stack recorded in CMAT. You can see how the results are similar. So we were very happy because we have proved that the technology is scalable and the results are similar in the laboratory test and also in the industrial testing. We also were able to prove the pressurization of the cathode, which is a very important parameter in this kind of device when they work in industrial application. And also we keep in a continuous working of 16 hours our device working at 0.5 ampere by square centimeter with a production of 0.5 kilogram of hydrogen per day, and we could see how the voltage tends to decrease in the continuous operation mode. So the final result is even much better than the original one in this polarization curve. As you can see here, we decreases the voltage from 2.12 volts to 2.04 volts. That means that the power density is less, so the hydrogen cost is also lower. So by summarizing, here we can compare our efficiency results. Here are those obtained in our laboratory. Those one are the obtained by the stack, and we can see that are more similar. And comparing the specific power consumption, what the recommendation done by the Clean Hydrogen Partnership, we can see that at low current densities we are near to the recommendation, but we need to improve a little bit more our catalytic coatings. And in this condition we can we prove our theory, and we were able to obtain almost or more than 1 kilogram per day at the higher current density rate of working. So all these data are regarding the electrocatalytic performance, but what about the stability of this kind of catalytic coatings? We performed a 45-hour continuous working methodology by a chronopotentiometric method, and we can see that in our laboratory the degradation rate of our catalytic coatings is around 1.75 millivolts per hour, which is pretty much compared with the literature. So with different studies, we determined that one of the causes that promote this degradation is the oxidation of the electrode for the oxygen, the anode, when it's working in oxygen evolution reaction condition, suffer an oxidation that promotes the segregation of iron, and we determined that probably the increase in the iron amount during the working conditions promote the desactivation of the catalyst. So here we think about an alternative to solve this problem for the anode, and we developing a bilayer catalyst coating, which is the original title of this presentation, by the modification of the magnetron sputtering conditions. Here you can see 3 examples of the catalytic coatings that we prepare. If we want to prepare a metallic catalytic layer, we use argon as a sputtering gas to obtain metallic nickel iron, and we try to oxidize our catalyst under the vacuum condition to promote the formation of a more stable layer. So we prepare metallic nickel iron, oxidizing nickel iron, and we also prepare the bilayer one to compare the behavior. So in the paper, there is much more information about how we developed this bilayer catalyst, how we tested it to prove that effectively the most active and also the most stable catalytic layer is the one that combines both layers, the metallic and the oxide one. And here, to summarize, I have compared its behavior with the original monometallic, monolayer metallic nickel iron catalytic coating. We can see here in the voltage current density representation how the voltage are shifted to lower values. So we are improving the performance of the catalyst. And also the more important property is that the combination of both catalytic layer, the oxide and the metallic, improve significantly the stability, decreasing the degradation rate under the 1 volt per hour of voltage increase. That this value is more correlated with with those values that we can find in the literature for this kind of catalytic coatings. So the final test was to prove it in our small prototype, and we tested by a continuous working methodology and 0.5 I didn't put it 0.5 ampere square centimeter of current density, and we can see how by working 5 hours by day during 5 days, we can see how our system is stable even the current increase from the 4th day, and we have a very stable behavior with a pretty value of voltage. So in conclusion, we have proven how magnetron spattery can be used for the preparation of catalytic layer in both the laboratory and the large scale magnetron sputtering chambers. Also, we have proven how this electrode can be used in large scale prototype with a bigger amount of hydrogen production rates with successful results. And finally, we can also we have also proven how we can modulate the composition of our catalytic coating to obtain different alternatives that can help us to improve the catalytic activity and also the stability of this kind of catalytic coatings. So that's all by my side. Thank you so much for your attention, and also I would like to say thanks to Paco, Agustín and Jorge por acogerme aquí durante estos 2 años. Thank you so much.
Muchas gracias, José Manuel, por la charla.